Okay, so we've heard a lot about some of the astronomical challenges, and I want to return to some of the statistical and maybe sociological challenges. And this lecture draws heavily on some material that I found Tom Laredo summarizing very well, and so I tried to make use of that. My overall goal is to improve the quality of your science, and maybe our science as a field, because there's a lot of sloppy methodology out there, and hopefully we can cut down on it, and hopefully we can recognize it when it occurs so that we don't then get distracted and spend years of our life trying to explain something that we never should have believed in the first place. And so I hope to increase your awareness of better methods for model comparisons than p-values, and hopefully thereby help the next generation do better than ours has. So maybe first, why do we do astronomy? Why do we look for exoplanets in the first place? I think for many of us, it's because it's fundamentally interesting. We want to learn about nature. Okay, so that's great. If we want to learn about nature, we should want to learn about the actual nature and not fool ourselves. If we want to train the future generations of scientists and engineers and policymakers and everything else, we should train them to make good inferences and not bad inferences. And if we want the public to trust scientists, both about exoplanets and about anything else that's important, we need to demonstrate that in a field that has very little perverse incentives. We don't have big pharma trying to make money off of drugs. We don't have trying to change the whole way the world runs on energy. If we can't get exoplanets right, how can the public trust us to get anything right? So it's really important that we set an example for science as a whole, I think, of doing good science. Maybe some of you have been so focused on your own research, you may not have realized that actually the past several years, there's been a bit of a credibility crisis in science. The movement towards reproducible research has really been driven largely by the life sciences, a little bit by the social sciences, where there's studies pointing out how often published research is wrong. And often it's because of things like shoddy statistical practices. And sometimes it may be, perhaps the most egregious examples involve someone maybe doing something, intentionally. But I think the vast majority of the mistakes are not someone trying to do something wrong. It's people fooling themselves. And so I don't want to fool myself. I don't want you to fool yourself. We want to try to improve the enterprise of science by doing a better job. Okay, so there's many aspects to reproducible research. There's things like being able to describe your methodology in sufficient detail that someone else can understand it and reproduce it. There's things like availability of telescope time, which is a really hard problem to solve. But the one about using valid statistical inference is among the easiest, lowest lying branches, and yet it's still one that we struggle with. So let's try to tackle that one. If exoplanets were subjected to the same scrutiny that the life sciences and social sciences have received the past several years, do you think Ardent's claims of exoplanets and exoplanet atmospheres would survive that level of scrutiny? I don't. I think many of our cases would sort of fall short, and I'll show you why. So what does it mean to discover a planet? What have people... Well, the old-fashioned frequentist way was that I considered a universe where there were no planets, and I said, well, if there were no planets, how often would I have gotten my data? And if this data isn't consistent with no planets, it must be consistent with planets. And that was the sort of A-B choice, one or the other. And I'll explore that in a little bit more detail. And I'll sort of try to push you towards an alternative way of thinking about it, where you weigh the Bayesian evidence of two models or more models and compare whether your information after taking your data now favors a model with a planet or an alternative model. So in the frequentist context where you're trying to reject the null hypothesis, what are we really doing? So a key concept in this is the p-value. And so what we do is we have some distribution of a test statistic shown here in blue, and we imagine a world where there's only this sort of null model is the only thing going on, and then we ask, in that world, how often would we get a p-value this test statistic as extreme as some critical value? And then we use that to either accept or reject the null hypothesis. And so it has some appeal to it, it makes some sense, but if you ever use a p-value, make sure you think 3 times and look back up and look at a 4th time at what it really means, because most of the time it's used, I think it's used wrong. And so to really be pedantic about it, if you have a world where there's no exoplanets, right, and then you choose where to set your threshold so that you would wrongly claim to detect a planet some fraction of the time, you're saying that this data would be judged to be a detection, and that the data that's doing it would be among the weakest data that's possible to provide evidence for that planet. Okay, that's big, long, and complicated. We don't want to write that every time in our paper. So if you must use a p-value, just call it a p-value. Don't call it something else. Okay, but when you do, realize that if you try to simplify it for your reader, and I'll just make it simpler, most of the time you lead to misinterpreting it. And perhaps the most egregious example in our field is people love calling it a false alarm probability. Okay, it's not a false alarm probability. So let's try to get away from that. And so Tom Laredo picked out some quotes of examples in literature. The authors have been hidden to protect the guilty. Star names have been redacted. Signal-to-noise ratios have been replaced. But the basic idea is this really does happen. So if maybe you think, oh, my senior colleagues would never do something so silly. No, they do. And we do it not just like occasionally. It's probably most of the time. Okay, so we really as a field need to sort of get away from statements like this, where we say the false alarm probability of some detection is some fraction based on a p-value. So what's wrong with this notion? Well, one thing to realize is the p-value is a property of not the signal, but of your analysis method. And further, your analysis method was based on the assumption that there was a world with no planets. And so it's not a false alarm probability of 10 to the minus 3 or whatever. Either the signal was or was not. For any signal in there, it's a false alarm probability of 0 or 1. And so if you try to say there's a probability that's less than 1, there must have been an alternative. But yet your first assumption was there was no alternative. So there's really a crazy way to sort of try to do science. It was maybe excusable decades ago when we couldn't compute anything useful, but now that we can, we should go beyond it. So why do people even, what is the value of a p-value? The sort of nice property of it is that under this null hypothesis, it's uniformly distributed 0 to 1. And so that's sort of the one good thing. And so it gives you some measure of how surprising it is under your null hypothesis. The problem is it doesn't give you an idea of how surprising is it under your alternative hypothesis and whether that's any better. And so oftentimes when there's a low p-value, it also means that your alternative model is also unlikely given your data. And so it's very easy to misinterpret. It does not pay attention to the probability of the alternative, such as there's a planet in my data or there's another planet. And so another thing is it often overstates the probability of this alternative because of this. And you can show that's not just some crazy, statistician counterexample. It's most of the time. And it's inevitable. It's just a matter of probabilistic logic. And so we want to sort of go beyond that. But I think some fields, maybe really some journals, have started to get grasp around this problem. So here's one, Basic and Applied Social Psychology. It's not the best journal in psychology, so it doesn't represent the entire field moving beyond it, but it's at least some journals are trying to go beyond it. And basically they said several years ago, we know p-values are being misused. Please don't do it. That didn't work. And so a few years later, they said, you know what? We're not going to take papers that do that. And so some journals have taken a strict line. I might even say the pendulum may have swung a little bit too far. But perhaps it's excusable because it's so hard to change fields with ingrained practices. If you're interested, I mainly put this up for the slides online if you'll want to learn more about the issues and look them up, several good references. Okay, so despite years of saying things like this, it basically has made very little inroads in the field. So I'm going to try to demonstrate with a very simple example of just how bad p-values are for rejecting the null hypothesis. So here we'll consider a nice model where we have every measurement is equal to a mean value plus some noise. Well, just simple standard normal noise. And there's a null hypothesis that the mean that it's centered on is 0. And so then you can make a test statistic that's based, I did the same thing. Test statistic of just your average value of taking several data points divided by the uncertainty. Here we're assuming the uncertainty is known. and root n. So that you can sort of think this as analogous to, I'm looking for an exoplanet, I'm asking is my signal 0, or do my points have some dispersion due to that exoplanet? And so in this case, the model's simple, so you can calculate your p-values analytically and do proofs about them, and it's a relatively good case. And so in some fields, some of the social scientists fields, they really get excited about a p-value of 0.05, 5% as being significant. I will say that the physical scientists tend to be a little bit more responsible. They kind of know like how that intuitively it just gives them bad results so often they shouldn't believe it. But then what they do is, instead of using the correct methodology, they say, well, I'll just demand a p-value is even smaller, right? And so maybe an astronomer might be excited about a 10 to the minus 3 p-value. Or maybe if you're a particle physicist, you might say, I want a 7 sigma result, 10 to the minus 12, right? But it's kind of silly, right? Because basically I know this method is so bad that I'm going to try to push it in one direction to make up for how bad, but it becomes totally unprincipled at this point. It's basically just making up an ad hoc procedure. And so we sort of use this to gauge how significant our result is, at least in some, I think, qualitative sense may be reasonable. And so we want to test this, like how does this work in practice? So imagine we can do Monte Carlo simulations, we can generate a bunch of p-values from a large number of tests where we know truth exactly, and then we can look at how often is the null hypothesis true, how often is the alternative hypothesis true. And so in a simple case, we'll show results where the null hypothesis is true half the time, the alternative is half the time. This kind of being generous, right? Because oftentimes when we're looking for rare events, the null hypothesis might happen much more than 50% of the time. We're looking for the rare case that has an Earth analog planet. And then what we'll do is we'll take only the subsets of Monte Carlo realization that have their test statistic within a narrow range. So centered sort of on a 2 sigma result, centered on a t-statistic of 2. So that would basically be where we'd be rejecting things about the 5% level. And then we can ask, for all those cases, how often was the null hypothesis true? And we can do it for different significance levels. So we have to pick some alternative or else to have this make sense. So in this case, consider a relatively benign alternative where we have things centered on 0. We just have a larger dispersion than the measurement precision. And we'll just, again, choose 50-50 of each, simulate our data, calculate a bunch of t-statistics, and then we'll bin up the different p-values, and we'll look at how often the 2 alternatives occur. And so the top panel here is on a scale of 0 to 1. The middle panel is from 0 to 0.1. The bottom panel is from 0 to 0.01 in terms of the significance or this p-value. And then the 2 bars are, we have in gray the null hypothesis. So this is that the mean really is 0. And then the dash bars is the alternative that the mean was drawn from this alternative normal distribution. And so we look at how often, sort of the ratio of times where the null hypothesis was true relative to the alternative hypothesis, and you can see that out here where you have very low significance levels, that the null hypothesis was true most of the time and the alternative was true rarely. But then as you start looking in this tail, you start zooming in, say at maybe 1 sigma, 2 sigma, 3 sigma-ish significance levels, you can start to see that even when we're here around a 2 sigma significance level, that the fraction of time where we had a null hypothesis and the fraction of time where we had the alternative hypothesis are about comparable. So we think the p-value is 0.05, but that doesn't really help that much. Because we have an alternative, and getting that small p-value is just as likely under the alternative model as is under the null value model. And then here are a couple of slides just showing as we increase the number of observations, you might think, well, if I just increase my observations, things will get better. No, right? They don't, right? So as I increase my observations, now I start to say, well, I could find a planet at 10 to the minus 3 level, right? So you can get excited down here. But you can see the same thing basically happens, right? As I take more observations, now a 10 to the minus 3 that sounds pretty good is basically just as likely under either the alternative or the null models. So if you're still a little skeptical, you can go through and work through this example. Jim Berger has a nice paper where this was drawn from, and sort of really laying out both the shortcomings of the p-value for making model comparison when you have multiple models, and then some ways to try to improve upon it. So what did we learn from all that? Well, a p-value can be useful for recognizing when your null model is not a good description of the data. That's very different from saying when an alternative model is a good description of my data. And so we want to realize that we don't want to say reject the null model and decide, oh, it must have planets, because this will dramatically overestimate the sort of the rate of false positives relative to what we expect, and that it's going to cause us, as our sample sizes get bigger, if we keep the same p-value, say a threshold of 10 to the minus 3 or 10 to the minus 7, whatever you want, this problem still rears its head. It's not something that will just go away with more data. And well, you can see that this is not a contrived example. So in the Berger paper, he works out and shows there's actually that's a subsequent paper. Sorry, it's this Edwards and Berger and Selke paper demonstrates that this isn't one crazy case picked to make this look bad. There's actually, you can show minimums on how badly it does, right? And there's minimum rates so that even under better cases, the rate at which you sort of get falsely accepting the alternative model is grossly exaggerated relative to what you might think from a naive interpretation of p-value. Okay, so now let's return to this question of what does it mean to discover a planet? And for 2 decades, or at least 1 decade, this was working pretty well, right? Our whole field of exoplanets was basically built on this for the first 10 years of radial velocity planets. So why did that work? And so perhaps the first thing to realize is that in the early days, they were looking at stars for the first time. They had made dramatic technological improvements to be able to measure velocities very precisely. And the signals that they were finding were often many times larger than the measurement precision. So if you have a signal to noise of 100, you can kind of do model selection by eye, right? It's pretty easy to tell that there's a signal there. And so really, the use of these statistics was almost as much about here's a way to sort of put a number beside what I already know as it was to make a principled decision. And also, the surveys that they were doing, they picked the best stars. They picked stars that, oh, there's sort of, it's a nice, quiet, sun-like star, low activity. And if it's an annoying star, they just pushed it aside and said, well, that's kind of annoying. Let's go back to that later, right? Or leave it for someone else. And so when we didn't have many alternatives, right? Well, then it wasn't such a big problem. And then perhaps the other thing was astronomers were paranoid. They basically said exoplanets had such a bad history prior to the 90s of false detections that people were justifiably skeptical. And so they said to overcome that, we need to be very responsible and make sure we get it right. And so they were basically paranoid. And maybe it wasn't paranoid through the use of statistics, it was paranoid through the use of common sense to say, if I'm not sure, I'm going to collect more data before I claim to have discovered a planet. Okay, and that general philosophy can be quite good when it's practical to collect enough more data to solve the problem. And so why should we change from this? Well, now we want to find planets with signals of a few meters per second or a tenth of a meter per second, right? So small signals. We're no longer in this luxury of humongous signal-to-noise ratios on every measurement. Further, our best stars aren't necessarily quiet, well-behaved FGK stars. Maybe we want to look at the nearest stars because we want to find targets for a direct imaging mission to go image and take spectra of, and those nearest stars aren't necessarily quiet stars. Or maybe we want to target stars that were identified by the Kepler mission, and they're annoyingly faint. Right? So there's reasons that we can't always focus just on the best behaved stars, and so this means that stellar activity, instead of being selected against, in some cases is now getting its fair shake in the universe of a lot of stars have annoying stellar activity. And then finally, the amount of additional telescope time needed in order to sort of turn a borderline detection into a clear, overwhelming detection can just be impractical. And so the old line of, well, we'll just collect so much more data that it's clear, now is so expensive, it's not really a viable alternative. And we need to learn as a field to make use of data sets that aren't totally obvious there's a planet, but rather they're detections that require performing a statistical analysis to believe. And of course, that means that now, instead of our statistics basically being a thing to satisfy the referee to say we did it, it's now front and center in our own ability to decide, do we believe that there's a planet in our data? So given those concerns, I think there's a great reason to move towards using the Bayesian evidence of comparing alternative models. And so the sort of short version of the Bayesian evidence is quite simple in theory. You have some prior probability for your model parameters given a model. You have a likelihood, the probability you would observe a certain set of data given that model and those model parameters. And basically all we do is we just integrate over them. And then we calculate from that the evidence. Now, I said all we do is just integrate over them. The reason why everyone doesn't do this all the time is this integral is often hard. Okay. In 1 dimensions, 2 dimensions, maybe 3 dimensions, you just call some numerical quadrature and it works just fine. As you get to several dimensions, maybe you have to use some fancier techniques. As you get to 10, 20, 30 dimensions, this is really, really hard. And so that's why there's a reluctance, is that it requires you to both work a little bit harder, be aware of techniques, think of approximations, and think things through. But if you can do it, so for the moment, let's just assume that we have various methods to estimate the evidence accurately, well, then we can get a Bayes factor, which is sort of the ratio of the evidence for one model to another model. If I had some reason to a priori believe that one model was more or less likely, I could add a prior probability for model 1 or model 2 and add that to my ratio to get a posterior odds ratio, saying after I've collected my data, I've updated my prior information with the evidences, and here's my relative probability for the two models. And a key thing is we're comparing the probability of two models. We're not just saying one model is bad, so it must be the other. We're saying, well, how good is this under the two different models, and what's their relative posterior probabilities? Now, it turns out that procedure is not that different from what I showed you in this toy example. I was showing you sort of a Monte Carlo case where we could do everything and know the truth, and at the end say, well, compare the height of these two bars. That's how often, conditioned on you getting a certain p-value, the alternative model or the null model is the true model. I was basically walking through Bayesian reasoning, and it made perfect sense because that's what Bayesian analysis is basically probabilistic reasoning. And so we can interpret that Bayes factor is the same way in that Monte Carlo calculation. So there's sort of both the mathematical integral formulation, the sort of common sense probabilistic reason method. And so the key thing to realize when using a p-value is that you're not really comparing hypotheses, you're just rejecting one. And so often when you have data that are unlikely under one model, it's also unlikely under every other model. And your real issue is none of your models are any good. And that's not a reason to accept one of them as they must be true. So we want to be on the lookout for that. So the advantages of the Bayesian approach are fundamentally it allows you to answer questions that you want to ask instead of answer questions that a statistician told you were allowed to ask under a certain framework. And I much prefer that. And it provides a rigorous basis for many things. So the field's gotten very good at performing Bayesian parameter estimation, estimating the uncertainties under a given model. We sometimes make a serious effort to compare the evidence for competing models. In principle, we could do things like adaptive scheduling through decision theory, although that's, I think, a little ways off. And perhaps the best feature of this is you have to be very explicit about all your assumptions. And so if you made an assumption that I don't agree with, when you listed all your assumptions, it'll be easy for me to see. And if you sort of invent an ad hoc procedure to sort of do something, it's kind of hard to tell what all your assumptions that went into that ad hoc procedure are. So if I make a similar slide about how should I interpret the Bayesian evidence, it might go like this. In a world where we have exactly n possible models, where our knowledge prior to taking the data is given by the prior probabilities, the model that each is correct, the Bayesian evidence for each has been calculated to be the evidence for each model, then our knowledge of the relative probability of each model taking data is given by a simple expression. Here, instead of just two models, there's the possibility that it's many. So that's very nice, much simpler to understand and interpret. There are a couple of caveats. So this word exactly, right, is probably often not true. So does your list of models really include all possible models? For example, might there be activity as well as planets? Might there be supergranulation as well as activity, right? And so if your set of models doesn't include reality, well, you're always going to select one of your models, and that will not be reality. It's not a panacea. You still have to have a set of good models if you want to make good conclusions. And the other tricky part here is I say the Bayesian evidence is calculated. And even though in principle that can be, sometimes it's quite a substantial undertaking. And so the computation of those integrals can be annoying in high dimensions, particularly is why it becomes problematic. Sometimes it's computationally expensive. Sometimes iterative algorithms converge very slowly. And as you go from, say, Markov chain Monte Carlo, which is very good for parameter estimation, even in pretty high dimensions, to calculating the evidence that requires integrating over that, there's an extra level of integrals. Those integrals are harder. If you actually want it to do things like calculate a utility, you have yet another set of integrals, gets even harder. And so putting this into practice can be significantly non-trivial. So what are some ways that we can do it in practice? What are practical ways? Well, instead of having an ad hoc procedure, I can try to estimate what I actually care about with different numerical methods for estimating them. So if I had a choice, I would love to use the Laplace approximation. The Laplace approximation is often a very good approximation. If you go back to your quantum mechanics class, this may have been known as the WKB approximation. Basically, it's taking an integral that has something like e to the function, expanding about the maximum of that function. At the maximum, the first derivative is good as 0. I just have some second derivatives. So then I have pull out my base value, second derivatives here in the integral. This now looks like a Gaussian integral. I extend my limits of integration from being from a to b to minus infinity to infinity, but it doesn't really matter because by the time you're far away from the integral, it all goes to 0. If you have at least a unimodal density and it's a nice strong mode, then the Laplace approximation can be very good. There's, of course, a higher dimensional version where you have to calculate the determinant of the Hessian matrix, basically the matrix of second derivatives of your function about the mode. So we can do that on either the likelihood or on the posterior probability, preferably including any priors. And this is a very good approximation, and it works well basically if your target density is nearly Gaussian. So if you have enough data, then eventually your target density might approach Gaussian, and then you can use the approximation. Things work pretty well. Now, if you don't have enough data and there's multiple modes, clearly integrating just around one mode isn't going to do a good job approximating two modes. So if, for example, in that periodogram we saw, there was another peak at a third or half the highest probability peak, if we just expand up one peak, we're missing the other one. Maybe we can make up for that, right, by doing our integral, expanding up both of those peaks and adding them together. So we could sort of kludge together some other variants to try to cover multiple modal situation if we can find all the modes. The other cases that can be problematic would be if our chi-squared surface here, instead of being one nice function that's nearly quadratic, if we have lots of little bumps, what we might really want to do is to capture this overall trend, but these little bumps would cause my evaluation of the second derivatives here would give me a much steeper function and cause me to misestimate the width of that mode. Similarly, if I had a function where there was a very sort of gradual rise in the tail, and both of these are realistic cases that occur for real exoplanet data. Here we have sort of the inevitability of lots of local minima in situations where you have data that hasn't quite identified the final mode, maybe in eccentricity and pericenter, maybe in period. Here we have the case often you have with long period planets where you have a very strong limit on the minimum orbital period, but a much weaker limit on the maximum orbital period. And so if I were to approximate these surfaces as quadratic, this one might do fairly well, but this one over here, well, I would sort of cut out all my probability that it's on a longer orbit in that tail. So there are cases where the Laplace approximation works very well. There are also cases where it doesn't work so well. Then there's some other methods. There's a likelihood ratio test. This works fairly well for nested models in some cases. There's several variants of it. You can either interpret it in a frequentist or a Bayesian way, depending on whether you account for your prior probabilities and whether you marginalize over things. But it basically gets, the spirit of it is there. And then perhaps the thing I see most common in the literature, if you're trying to do a good job, they're really trying, is various penalized likelihood methods. So perhaps the most famous is the Bayesian information criterion. It sounds very Bayesian. It's in the name. It's basically a con. It's not really Bayesian in hardly any way. And then there's another one. I don't know how to pronounce this. AIC, I don't know. Information AIC, BIC works a lot better. And we'll see that they have some features and when one is better than the other. So the Bayesian information criterion here, basically what you do is you take the best fit value, the likelihood, the best fit location. Maybe you make it a little better by using the posterior and counting for your prior as well. But then you have a penalty term that has to do with a number of parameters in your data and the log of the number of observations you have. And so if I compare two models by subtracting the BIC for each model, then I can compare both the maximum likelihood value and something related to the number of model parameters. The problem is, at least in the naive, the standard form, it ignores priors, both of the model parameters and the priors of the two models. It ignores the steepness or the shape of the likelihood. Remember, the Laplace approximation, I was trying to integrate over that minima, and in this case, we totally ignore the width or the shape of it, and also any other mode. So this can be useful if the priors over the models are so close it doesn't matter, if the prior over theta is so flat that it doesn't matter, if your likelihood really is very nearly Gaussian where it is, and they have similar widths, and there are no other modes. So if all those criteria are met, this would be a good thing to use. My guess is you don't know that those are all true, and so why would you want to use this? There's another one, the AIC, that's also used. It's basically the same key feature, the log of the maximum likelihood. It has a different penalty term. In particular, it doesn't include the number of data points, rather just the number of model parameters. So if you think about asymptotically, as I get more and more data, these two criteria will perform very differently. Right? With my BIC, going back here, I had, as I increase the number of data points, the penalty for the model with more parameters will become more and more severe, whereas for the AIC, my penalty does not become more and more severe as I get more observations. So if I have actually, I got this wrong, didn't I? Sorry, this should be AIC. I should change this. This is right. The AIC is better than BIC. Sorry. But for two common cases, one is if you want to use prediction, you're not really trying to find what's the truth of the universe. You're trying to choose which one to use for predicting things. You can show why the AIC often works better in prediction cases, and also in high-dimensional problems. In other words, where your sort of number of parameters here is quite large. You can see that if your true model isn't among the set performed, there's some asymptotic limit where it gives you a good discriminatory power. The problem is your asymptotic limit is rarely reached. So the fact that it does better in a case that's not applicable to you is of limited value. Another sort of cute demonstration that all of these are fundamentally flawed is if I take a scatter plot of, say, x versus y, and I ask, let me find my maximum likelihood value for this, and I'll compare two models. Well, I can come up with a three-parameter model that fits all the data points exactly. A simple sine curve, just make it really high frequency. It goes through all the data points, right? And you all laugh because you know this is stupid, right? And so why do you know it? It's because, well, in order to make that work, I would have to tune the period so ridiculously precisely to make it go through all the data points. That's what a Bayesian calculation penalizes, is when the ability to choose that parameter requires me to tune very precisely. That Laplace approximation, that width of there, would be so narrow that this solution would be dramatically penalized, and something else that has a much broader range of allowed parameters but doesn't go through all the data points exactly could still be the favored model. So any method that only uses the maximum likelihood value is subject to these sorts of problems, and if you want to be a little bit snarky and have an annoying referee who says, why don't you use a maximum likelihood method, you can sort of come up with some crazy example just to tell them Bayesian is better. So why do I even tell you about these if there's so many problems? Well, there is value in these. They're not totally ridiculous. They're very easy to calculate. You can calculate them easily, quickly, and that's worth something because sometimes you have finite time. Right? You can't do everything perfectly. It's a lot of work. You have to choose. Where is it worth devoting my effort to calculate one of these things well? And I think it is reasonable as a sort of first pass in deciding which planetary systems do I want to sort of devote my attention to decide to publish next. I might use something quick and dirty to help me set my priorities straight. And then once I do that, then I can complement it with a real calculation. And so I wanted to sort of be careful, though, remembering that these basically are arbitrary criteria because the asymptotic limits in which they make some sense are rarely met for our real problems. So if I can come to some suggestions for best practices, Eric had a very good list yesterday about sort of the steps in the scientific process or statistical analysis process. I would add one more, and that is to analyze data sets generated with your model before you analyze real astronomical data. If your method doesn't work on data where you know exactly all its properties, it won't work in the real world. Now, if it does work on your data where you know the truth, doesn't mean it will work perfectly in the real world. But if it fails here, you know it will fail. And you don't have to just give up. You can not just validate your model or fail to validate it. You can then tweak your method, understand why it didn't work, go back and prove it. And then once you've validated your method so it works, doesn't have bugs, the algorithm is sound, it converges in a reasonable amount of time, then you can apply it to your astronomical data. In the case of exoplanets, we have several sort of challenges. For example, stellar activity has gotten a lot of attention here. As Eric pointed out, if we actually want to characterize stellar activity, it's not just good enough to have some little fancy model. We have to have lots of data so that we can empirically understand that data. If we want to say something rare happened based on empirical evidence, we need to have a large sample size. So if you want to say that some star only does something 1 in 10,000 times, you have to look at 10,000 stars. And perhaps the most dangerous thing I've seen is people doing ad hoc revisions to their model based on an initial analysis of their data in question. So let's try to avoid that. I see I'm running a little low on time. Basically, we want to use principled algorithms, test for non-convergence of iterative algorithms like MCMC or these integration methods, and test the sensitivities to prior to likelihood conclusions. And in summary, what that gives us is that we want to aim to do high-quality research, statistical sound. We want to avoid misinterpreting p-values, for example, as false alarm rates. And that's going to performing model comparison, discovering planets is going to require that we at least learn the fundamentals of how we would do Bayesian in principle, and then we can find practical approximations that can be good uses for our problem. And that can be a little field among itself. And then I'll end during the question section with an advertisement for a SANC Program, a year-long program where statisticians and astronomers will work together. If people are interested in thinking about some of these questions there, feel free to contact me, Angie Wolfgang, Jesse Shizeski, and is there anyone else there? Maybe all three of us here now, but all three of us can give you more information about that program. Thanks. I'm glad you asked. Sorry. So the question was, there's this code out there, MultiNest, that claims to do this. Why don't we all just do that? A few reasons. One is there's no proof that MultiNest works. It's basically an ad hoc algorithm that sometimes works well. So if you go to the trouble of validating that the estimates it gives are very good for your problem, then I could understand using it for, say, other variants of my problem with slightly different data over and over and over again. In cosmology, for example, they've basically done this, right? They've said, well, we've applied MultiNest to solving the cosmic parameters. We've compared it to other methods. It's faster and better for this problem. And so then they can update their data set, use it over and over again. I think that's a reasonable use of MultiNest. The problem is, if you just use it to a new problem where you haven't validated that it works, you calculate something. On the spectrum of things I showed, I think it was probably among not the worst, but I don't really know what I've calculated. And that's why I'm sort of reluctant to use it in cases that hasn't been validated for.
So another technique I've seen to use packet errors is the Savage-Dickey ratio estimators. Just wanted to hear your thoughts on that.
Yeah, so the question was about what about the Savage-Dickey density estimator, Savage-Dickey density ratio estimator. So you can Google it if you want. It's very nice if you have nested models, meaning that, say my no planet model is a subset of my planet model where the amplitude of my planet is 0. Right? An example of a nested model, because I have a parameter value in the more complex model that reduces to the simpler model. If I have nested models and my number of dimensions differs by 1 or 2, this can be a good method for doing model comparison. If it differs by more than, sometimes even 2 or more, sometimes it struggles. The other sort of annoying thing is, when the evidence is really strong for something, and by really strong, it only has to be, say, 10 to the 4 to 1, which happens fairly often, then basically you have very few samples near where the more complex model reduces the simple model, and so your estimate is very poor. So when you actually do have strong evidence for something, you just want to document to the referee, see, there's really strong evidence for this. It takes a ridiculously long Markov chain to get enough samples to show that it's really rare. So it kind of degrades almost to like a qualitative estimator. But I did this Markov chain for 10 million iterations, and I didn't get any near here, so clearly it's very rare. So I think it can be good, but it almost often becomes qualitative in many cases. When it is useful for quantitative estimates, it's often useful in the sense of, saying two things aren't so one is not so much more likely that I really want to make a strong conclusion for it, right? So then I might get, oh, well, there's a 10% probability for one, 90% one, 10% the other. Maybe that's good. I've quantified it. I know it. I recognize it. But then it's sort of, often you wouldn't necessarily want to go out and say claim a planet based on that. But it'd be great if you use that to say, here's a data release. We've gone through all our systems, and we've now selected, flagged those where the detection is clear because we can't even estimate it reliably. Here's the ones where we have a decent Savage-Dickey density ratio estimator, and it's 10, 20, 30, so people could draw say their own thresholds to make a catalog. I think that'd be a great use of it. Yeah, so the question there was about how do you know that the true model is included in your list of models you're considering? And of course the answer is it's probably not. The pithy quote is all models are wrong, some are useful. So we're not really necessarily asking that our model be perfectly right. We want to know, is our set of models useful? And I say, arguably part of the definition of useful is when I perform model comparison, I learn something that's actually reflective of the universe rather than just my fun little statistical models. So, I mean, in the old days when we basically had planets that were so big there was kind of no other alternative. For example, it was really easy to say, oh, there's the 0 planet model, the 1 planet model, the 2 planet model, the 3 planet model. Hey, I've got every integer between 0 and 4. Now that we have to worry about stellar activity, different kinds of stellar activity, our model of stellar activity isn't perfect, it's a lot harder. And so it does come down to you're constructing a model and you're computing probabilities within the context of that model. But that's inevitable, right? No matter what you do, you're always going to have a set of assumptions and say, these are calculated within my set of assumptions. So I say that's sort of where you as a scientist and maybe a referee sort of can sort of try to argue, here's why I think there's a reasonable conclusion. They might come up with, well, what about this other one? Okay, I've added a new model to my ensemble, and here's what happens. Or maybe I do a sensitivity test where I say, I'm going to add another parameter and marginalize over that or perform sensitivity tests. So ultimately, statistics does not solve all your problems. It's merely a tool for calculating, probabilistic inference. And you still have to have some... Yeah, use your brain in science. Sorry.
All right, let's thank Eric.